Welcome to our deep dive into the Mandelbrot set. I know you, our listeners, have STEM backgrounds, so I think you'll find this fascinating.
It certainly is captivating. The Mandelbrot set really shows how simple rules can just create incredible complexity.
Absolutely. It's beautiful to look at, and the math behind it, while it can get pretty complex, is built on a surprisingly simple foundation. So how do we even start with something like this?
Well, we can start with a bit of history, believe it or not, but the Mandelbrot set wasn't actually discovered by Benoit Mandelbrot.
Oh, really? I was expecting him to be the main player from the start.
He's important, but the story really begins earlier in the early 20th century with two French mathematicians, Pierre Fatou and Gaston Julia. They were working on complex dynamics, which really laid the groundwork for understanding iterative processes in complex numbers.
So they were working with what would become the Mandelbrot set, but they didn't have the tools to visualize it the way we can today.
Exactly. It's like trying to understand a huge landscape, but you're in the dark. They had the math, but they didn't have computer graphics to help them see what they were working with.
Then, in 1978, Robert W. Brooks and Peter Metelsky came along. They were the first to actually define and draw the Mandelbrot set. But they weren't even studying complex dynamics, were they?
Right. They were studying Kleinian groups, which seem totally unrelated. It's fascinating how different areas of math can, intersect in such unexpected ways.
Absolutely. Their initial drawing of the set wasn't that great, though, was it? Because they were limited by the computers at the time.
Right. It wasn't until Benoit Mandelbrot entered the scene that the set was really brought to life.
So this is where Mandelbrot finally comes in.
Yep, in 1980. While working at IBM, he used computers to visualize the set, and in a lot of detail, for the first time. His work really showed the intricate and self-similar beauty of the set, which helped to popularize fractal geometry.
I bet his visualizations were a game changer. This abstract mathematical object suddenly became this tangible, beautiful thing.
Exactly, and that's what sparked interest in the Mandelbrot set and its implications.
But I'm guessing the story doesn't end there.
Not at all. In the mid-1980s, Adrian Dowdy and John H. Hubbard began a formal study of the set, a mathematical study, and they were able to prove that it's connected, so it's all one piece, which went against earlier ideas that it was fragmented.
So this infinitely complex object, born from such a simple equation, is actually all connected.
It is, and it's actually Dowdy and Hubbard who named the set after Mandelbrot, acknowledging his work in popularizing it.
Interesting. So even though others had visualized the set before him, it was really Mandelbrot's work that made it famous.
Yeah, he helped to connect abstract math with the public's imagination. But let's get into the math behind this fascinating object.
Okay, let's unpack the equation behind it. It's Zn plus 1 equals Zn2 plus C, right? I know Z starts at 0 and C is a complex number, but how does it all fit together?
So it's all about iteration. You start with Z equals 0, and you choose a complex number for C. Then you plug those into the equation, you get a result, and then you plug that result back into the equation again. And you just keep repeating this process.
And what happens to the value of Z during this repetition, this iterative process, determines whether or not C belongs to the Mandelbrot set.
Exactly. If the absolute value of Z stays bounded, which means it doesn't get infinitely large, then C is part of the Mandelbrot set. If it escapes to infinity, then it's not.
So the set is basically all the complex numbers that don't make Z go to infinity when put through this process.
Precisely. And the way we visualize it is by giving each point on the complex plane a color based on how quickly or how slowly Z grows. This is called the escape time.
Okay, so different colors represent how fast those values escape toward infinity. So all those points that stay bounded, the ones in the Mandelbrot set, they're all probably the same color, right?
Right, those are usually black. And all those points outside the set are colored based on their escape time. And that's what creates those beautiful and intricate patterns that we associate with the Mandelbrot set.
So we have this simple rule, this iterative process, that creates this infinitely complex and beautiful structure. I'm hooked and ready to dive deeper.
Well, then let's explore some of the more interesting aspects, like the self-similarity and the points where that self-similarity is super clear. So one of the most interesting things about the Mandelbrot set is its self-similarity.
I've heard about that. It's like if you zoom in, you'll always find smaller versions of the set inside itself. Is that right?
Yeah, pretty much. When you zoom in on certain parts of the boundary, you'll see these smaller copies of the Mandelbrot set. They're not exactly the same each time, but they're very similar.
So not exactly like a mirror image, but more like echoes of the same structure, but smaller.
Yeah, that's a great way to put it. And there are these points, there's called Misiurewicz points, where this self-similarity is like really clear. Around these points, the mini Mandelbrot sets are very easy to see.
Wow. It's amazing that this complex structure repeats itself over and over, but smaller and smaller. It's like a mathematical Drost effect.
Exactly. And this never-ending self-similarity, that's one of the key things about fractals, which the Mandelbrot set is.
It's crazy to think that such a simple equation can create something so complex and infinite.
And we can't forget all the other mathematicians who have helped us understand the Mandelbrot set.
Yeah, like Heinz Otto Peitschken and Peter Richter. They really showed the world how beautiful the Mandelbrot set is.
Totally. Their pictures, books, and exhibitions really helped to make the set popular. They made it, understandable and visually appealing for people who maybe weren't into the math.
It's like they translated this complex math concept into something everyone could appreciate.
Yeah, exactly. And then there's Mitsuhiro Shishikura. He really helped us understand the fractal nature of the set. He figured out the Hausdorff dimension of the set's boundary.
Right. Hausdorff dimension. I saw that in the research, but I'll be honest, I don't really get it. What does that even mean?
Sure. It's basically a way to measure how rough or fractal-like a shape is. We're used to dimensions like 1, 2, and 3.
Right, the basic dimensions of our world.
Exactly. But fractals can have fractional dimensions, numbers that are like between the whole numbers. And Shishikura found that the Hausdorff dimension of the Mandelbrot set's boundary is 2.
Wait, so even though it looks like a line, it's so complex and wiggly that its dimension is the same as a plane.
Yeah, you got it. That's what makes fractals so cool. They don't follow the normal rules of dimensions. And that's just one example of the deep mathematical things we've learned from the Mandelbrot set.
So this object has shown us a whole new way to look at geometry and dimensions.
It really has. And then we have Jeremy Kahn, who proved, using topology, that the set is connected. This really solidified our understanding of it.
Wow, this one mathematical object has led to so much research and discovery.
For sure. And we can't forget about Julia sets, which are really closely related to the Mandelbrot set.
Oh yeah, I've seen those.
Hmm.
Julia sets are incredibly detailed too. How are they connected to the Mandelbrot set?
Well, every point in the Mandelbrot set actually represents a specific Julia set. Imagine you pick a point, C, in the Mandelbrot set, and you use that in our equation.
So instead of changing C to see if it's in the Mandelbrot set, we use it to make a different set.
Exactly. And the kind of Julia set you get, its shape and how complex it is, depends on where that C value is in the Mandelbrot set.
So the Mandelbrot set is like a map of all the possible Julia sets that could be made with that equation.
That's a perfect way to think about it. Every point in the Mandelbrot set is like a seed that grows into a unique and often very beautiful Julia set.
It's crazy to think about the connections between these mathematical objects. And they all come from the same simple iterative equation.
I know. And this really shows the beauty and surprising interconnectedness that can come from simple mathematical rules.
I could already see how the Mandelbrot set might help us understand complex systems in the real world. I feel like we've only just started to explore this incredible mathematical object.
Yeah, there's always more to uncover with the Mandelbrot set. It's like a universe of infinite complexity.
Makes you wonder if something like this, made from a simple equation, could help us understand complex systems in the real world.
That's a really interesting thought. There's been some discussion about whether the Mandelbrot set and fractal geometry in general could give us some insights into understanding how complex systems in nature work.
Like how coastlines and snowflakes and even like the branches of trees, they all have those fractal-like properties.
Right, exactly. Those natural things, they show self-similarity across different scales, just like the Mandelbrot set.
But is there more to it than just, looking similar?
That's what scientists and mathematicians are trying to figure out. Some think that fractal geometry could be a whole new way of looking at complexity in fields like biology, physics, even economics.
So the idea is that the Mandelbrot set, this purely mathematical thing, could hold the key to understanding how complex systems in the real world actually work.
It's possible, and people are researching it. It really shows how math can unlock secrets in unexpected places.
Even if we're still figuring out those connections to the real world, the Mandelbrot set has already had an impact on other areas, right?
Oh, absolutely. It's influenced computer graphics, art, and music. Those amazing images have inspired artists and designers, and the algorithms used to create them have been used to make realistic landscapes and special effects.
It's a good reminder that math isn't just equations and formulas. It's also beautiful and inspiring.
Definitely. The Mandelbrot set is a perfect example. It exists entirely in math, but it has this captivating power that goes beyond any one field.
This deep dive has been amazing. I feel like I understand the power of math and the beauty of complexity in a whole new way.
It's been great exploring this with you. The Mandelbrot set is a great metaphor for how interconnected and complex our world is.
It really makes you think. I bet our listeners will be thinking about the Mandelbrot set for a long time. It's given us all a new way to see the power of math and the beauty of complexity. So, until next time, keep exploring.